We have Dr. Gary Griggs from the University of California at Santa Cruz. He's a distinguished professor of earth sciences and the director of the marine sciences since 1991. He is also on the scientific advisory team of the California Ocean Protection Council and was a member of the very recent National Research Council Committee on Sea Level Rise in California, Oregon, and Washington. His research is focused on the coast of California and includes coastal erosion and protection, beaches, and the effects and impacts of sea level rise. I have had the great pleasure of seeing him present in the past, and I know you guys are all in for a treat. So without further ado, here is Dr. Griggs.
I don't think anybody knew where UC Santa Cruz was until John Laird became Secretary of Resources, because he went to UC Santa Cruz. So now we have something to be known for. So thanks for coming today and for the opportunity to speak. What I want to do is talk about the ocean side of climate change and adaptation. And most of the people in California live in coastal counties. Something like 80% of all the jobs are in coastal counties. So the coast matters to us, whether we live there or not. But there's a lot of problems along the coast, not only from sea level rise, but from extreme events. A lot of property now you can pick up fairly inexpensively along the shoreline because its lifetime, its half-life is maybe relatively short. Sea level rise is not a new thing, although we think of it today as something that's sort of more pressing than perhaps in the past because it's sort of a long, slow, gradual process. But this is just a plot of sea level rise over the last 350,000 years. So you can see on the horizontal axis is time with 350,000 years ago on the right coming towards the present. That's where we are today, which we define as zero. But if we had been here 20,000 years ago, sea level would have been 120 meters, maybe 350, 400 feet lower. So sea level has gone up and down repeatedly through geologic time, primarily because of the amount of heat we receive from the sun, and that's because our orbit, not only our rotation, but our irregularities in our axis of rotation, also the distance from the sun, changes over time, over some fairly regular cycles. So when you look at this, you can see there seem to be some patterns on roughly 20,000, 40,000, 100-year cycles. So sea level was changing long before humans evolved, and you can look back about 120,000 or so years ago and see that sea level was maybe 15 to 20 to 25 feet higher than it is today. So sea level has been much lower and much higher. The difference is there were no people around. And now we have built a good part of our civilization within a few feet of sea level. So how has the shoreline of California changed as sea level has risen? And this is a short, maybe 10-second video, and what you'll see is where sea level was, where the shoreline was about 18,000 years ago at the end of the last ice age, when about 10 million cubic miles of seawater was on the continents as ice in glaciers. And as that ice began to melt, the water flowed into the oceans warmed, and the ocean water expanded. So this is about 18,000 years of sea level rise. You can see where San Francisco is, where SFO is, and Sacramento. So this takes maybe 10 or 15 seconds, and you'll see how that's retreated, how the shoreline is retreated. You'll see the Farallones begin to appear out there, coming up to the Golden Gate about 8,500 years ago. Then ocean entered San Francisco Bay all the way up to Sacramento. And then sediment began to flow down from the rivers, from the gold rush, all kinds of things, and filled that back in again. So California's seen sea level rise and fall in the past. What's driving that today are primarily three things. The biggest factor, as concluded by this National Research Council committee, is ice melting. So that makes up about 2/3 of the rise we're seeing today. Another third is warming of water. So as we heat water, it expands. That's why on the top of your water heater you actually have a little space for when it gets hot. But as the ocean gets warmer, they're expanding. And so if the ocean average depth is 15,000 feet, we warm it by a degree or two, it's going to rise by meters. So ice is melting, putting water into the ocean is expanding. The third thing that's very local or geographically variable is what the land is doing. So if the land is coming up or subsiding, that's going to affect what sea level is doing at any one particular location. The land is rarely stable anywhere on Earth. And there are places where, like New Orleans, where the land is actually sinking. So sea level is rising at this rate, the land is sinking, so the difference is getting greater all the time. Northern California, parts of Oregon and Washington, Scandinavia, Alaska, the land is actually rising for several reasons. Sea level isn't rising as fast, so there's actually a gap. Sea level is actually dropping relative to land. So there's some places on Earth that are feeling this much more than others. If we look at California, most of our historic records on what sea level is doing has come from tide gauges. So we have instruments out. This is, say, the Golden Gate is one of the oldest in the U.S. And on the bottom you can see going from San Diego on the left all the way up to Crescent City, and then we actually have part of southern Oregon. That blue line, well, let's say the blue line has been the global average for the last century, about 8 inches per century, 1.7 millimeters per year. The red are the records from all the individual tide gauges. So you can see they vary from maybe 1.5 or 2 millimeters a year. Generally the range is 7, 8, 9 inches per 100 years. But if you look just north of Humboldt Bay at near Crescent City, and the numbers on the Oregon coast, they're generally much lower. And that's because that section of coastline is coming up. So most of California, from San Diego to Humboldt Bay, the coastline is characterized by the San Andreas Fault. So the coast is sort of sliding horizontally northwest towards the Aleutians. But from there north, we actually have a collision where one plate is going under Crescent City, Oregon, Washington, and actually pushing the coastline up, which means sea level rise in some cases is actually a negative, meaning sea level is dropping relative to land because the land is going up quickly. So things change for the very northern part of California. This is just one of those tide gauges, the oldest we have, which is San Francisco. Goes back to about 1850, 1855, and you can see this very regular increase at about 8 inches per century, roughly 2 millimeters per year in San Francisco. Globally, that number is now increasing, but we have to take a long-term look. If you just looked at a few years, it could be very deceiving because there are periods when sea level rises faster and slower, and I'll speak to that in just a second. So what are the impacts as sea level continues to rise? We can see today, and I'll show you some images, temporarily flooding. In other words, really high tide, sea level begins to rise, it starts to flood low-lying coastal property, and gradually beaches will be inundated. And I'll talk a little bit more about that because if there's nothing in the way, the beach will continue to migrate landward. And that's been going on since the last ice age ended 18,000 years ago. The coastline from that video was way out by the Farallones. As sea level rose, there were beaches there then. Those beaches migrated landward. But when we put a barrier in, a seawall, Ocean Beach, for example, they cannot migrate any further inland. So gradually our beaches will be inundated. Coastal cliffs, bluffs, and dunes will continue to retreat. Again, that's not a problem unless something is built on them. Coastal infrastructure, I'll mention that in the next slide. All the things we built, public infrastructure along the coast as well as private property. Also, we tend to increase seawater intrusion into coastal aquifers. And there's issues about wetlands that are sort of set at certain elevations. Can they respond rapidly enough to sea level rise? So sea level rise can impact existing development and proposed development. So we need to think carefully about anything new we build today. Do we want to build a $500 million sewage treatment plant right at sea level? We want to build those at the lowest spot in the community. So Wastewater runs downhill, but we don't want that to be inundated in 10 or 20 years. We can also affect public and private property. Public, all the things you can think about: streets and highways, parking lots, sewage, treatment plants, transmission lines, pump stations. Power plants have typically been built right at sea level because we use that seawater for cooling. Railways, airports, parks, etc. Private, all the things you're aware of: homes, businesses, commercial buildings, so forth. Anything built on the ocean is going to be impacted by sea level rise, depending on what elevation it was built at and how fast that sea level rises. A few examples, even at today's high sea levels, very high tides, Newport, Balboa Bay, some of the most expensive property in the state, this is high tide within a few inches of floor level already, without any additional sea level rise. Sausalito, Mill Valley, this looks like it's just a heavy rainstorm. That's actually ocean water coming from the bay at a very high tide today. Place many of you may know, the Embarcadero in San Francisco at very high tides is already awash. So whether sea level rises 12 inches or 24 or 6 inches, it's already in many places sort of right at the level where things are beginning to be affected. And Huntington Beach, I don't know whether they make Porsches to withstand seawater or not. I just love this picture. This guy kind of wondering, what's this guy doing driving through the ocean? But a lot of the coastal towns in Southern California were built right at sea level. We also have cliff or bluff retreat issues. This is in Monterey Bay, and one of the things I mentioned before, where there are no back beach barriers, no highways, no seawalls, no buildings, and sea level continues to rise, the bluff continues to erode, we will still maintain a beach. So if you look on either side, this is the old Soldiers Club at Fort Ord in southern Monterey Bay. On both sides of that building, there's a beach. They tried to save that building for a number of years by putting in a lot of rock. We've now lost the beach in front of that wall. We call that passive erosion. So wherever we have fixed the back beach with additional sea level rise, we're going to flood or drown that beach. When Fort Ord was closed and it was taken over by a number of state agencies and universities, that building was removed and the beach came back because we took out all the rock. So there is a way to bring back our beaches. In this case, it was relatively simple, but if it's a multi-million-dollar hotel, it's going to be a little more complicated. So we can remove those barriers, adapt, and allow that beach to continue. Here's another example in southern Monterey Bay. Monterey Beach Hotel, built well out on the beach initially back in the late 60s. As sea level has risen and the coast on either side has retreated, at high tide it now becomes a peninsula. So we're seeing also a loss of beach in front of that structure over time. If we look at Southern California, 1/3 of the entire coast of Southern California's 4 counties, San Diego, Orange, LA, and San Diego, has now been armored. So whether it's a seawall, a revetment, a bulkhead, something is there to keep the beach from migrating. Yet that's where our largest amount of beach visitors are. So this is a major issue we're going to have to come to grips with. But in addition to that gradual sea level rise, we also have these large or extreme events. Superstorm Sandy is one of those examples. That wasn't slow sea level rise. It was a huge storm with elevated sea levels. Katrina was another. So in California, it's been major El Nino events, 82, 83, 97, 98, 209, 210, when we have large waves, storm surges, and elevated sea levels coming at high tides that does most of the damage. 82, 83 was something like $200 million in damage. So water levels from those events can exceed sea level projections for the next 30 or 40, perhaps even 50 years. And those are going to be of greater concern in the short term. And because sea level is a ramp that seems to be getting steeper, those events are going to be on top of that background sea level, which is continuing to rise. Lots of places in California look great in the summer months. This is Mission Beach in San Diego in the summer. Nice wide beach. Houses are protected by a very low wall. Great place to invest. 1988 winter, we had very large storm combined with high tide. So the next photograph is taken from where that arrow is. Sometimes you can show a picture, you don't have to say anything. So what do? Well, that little wall didn't make any difference at all. And this is without any additional sea level rise, but it is one of these fairly extreme short-term events that's going to impact the entire coast of California. Seacliff, which is in the state park system, is a great place for recreational vehicles and picnicking, so forth. Very wide beach in the summer months. In the winter of 1983, this bulkhead had just been rebuilt about 2 months earlier. The waves overtopped that wall, and they overtopped it some more. At this point, I felt it probably wasn't a good place to be standing, so I left. Boy, this is the driest humor audience I've ever spoken to. When it was done, about half of that wall that was just finished had been taken out, but you look out in the surf zone, you could see 6 previous walls that had all been removed over time through previous storms, and they're moving back. So this is another one of those sites where we've got to think ahead and say, how many times do we want to rebuild this? Cliffs and bluffs will continue to retreat. This is Pacifica. Got a lot of recognition, I think, just because it's such a dramatic spot. People buying and selling these apartments right now, you cannot live in those. Another spot I like to use is, this is student housing in Isla Vista, UC Santa Barbara. It's a fun place to live, I guess. But they're kind of precariously perched out there on the edge, and I was just down there maybe a couple of months ago, and the front of that unit's been taken off. Houses continue to move back from that edge. So a lot of places where cliffs are eroding. We also have, not often, but some good examples of large landslides. This is in Torrey Pines, just north of La Jolla. Interestingly, in the background, you can see a big tower crane. Somebody's building a house right at the back of this headscarp of this huge slide. Immediately to the south, this is now the edge of the Scripps Institute campus. This is the National Marine Fisheries Service building. For some reason, was built right on the edge. And at the base of the bluff, you can see there's actually a big landslide mass. That building is now condemned. It's being taken down. And behind it, you can see a brand new National Marine Fisheries Service building being constructed. So large-scale landsliding led to complete demolition of a building. The NRC committee that put out their report a little over a year ago was asked by then Governor Schwarzenegger and the governors of Oregon and Washington, as well as a number of state agencies, to look at sea level rise for California, Oregon, and Washington for 2030, 2050, and 2100. And this plot, I'll show you something that maybe is a little more understandable, actually shows in blue Oregon, Washington, which is a little lower, California in orange, the global number in red, and then Vermeer and Romsdorf, who used a slightly different method. But you can see sort of the midpoint by 2030 is 6 inches of rise, starting at the year 2000, but the range is about 2 to 12 inches. 2050, about 12 inches is the average estimate or projection, but it could be from 5 to 24 inches. And by 2100, midpoint's about 36 inches, but it could be from 16 to 66 inches. Now you might say, well, why do we have those huge error bars? Well, there's the known knowns, there's the known unknowns, and there's the unknown unknowns. So trying to project sea level by 2100 or even 2050 is sort of like if you hadn't been born yet. How much money do you need to retire by 2100? 87 years into the future. Well, what are all the variables that go into that? What's the economy? What's property worth? What's interest rates? Sea level is like that. There's a lot of natural factors, and there's a lot of others like greenhouse gas emissions. What are we going to be driving? How much oil are we going to burn? But also China, India, and the rest of the world. So those estimates get greater, or the range gets greater as we go further out in time, understandably. So I thought of putting this another way. This is 2030. Here's the low and the medium and the high. Danny's going to get his pants wet here. By 2050, the midpoint's about 12 inches, but it could be as high as 24 inches. And by 2100, it could be as much as 5.5 feet. That's a lot of water. We now have about 150 million people globally living within 3 feet of sea level. They're going to have to move somewhere. A lot of people have seen this image of San Francisco Airport. At 16 inches, the runway goes underwater. Next time you fly out of SFO, just look at the water level, and I would just say water landing is probably not a good long-term solution. I showed the San Francisco tide gauge before. These short-term events, and you see these pulses on that tide gauge, these are El Nino events where sea level rose 10 or 12 or 13 inches for as much as 2 or 3 months at a time. So that takes up a lot of sea level rise at 8 inches or 12 inches per century, and those in the short term are going to be the things we got to worry about. So how do we begin to deal with that? Well, there's a few examples of places that we've learned something from about how not to deal with it. North Carolina had a state science commission, much like our science advisory team, that said they should expect 39 inches by 2100, sort of the midpoint we're using. Business development interests complained, saying those regulations would cost them too much money and restrict their development. So they legislated no more than 8 inches. But we don't get to vote on sea level rise. It's a natural process. Virginia, coastal scientists put out a report that said basically this is one of the biggest hazards we face. Virginia lawmaker says sea level rise is a left-wing term, and they took it out of the report and decided to use coastal flooding. Virginia is suffering from sea level rise. So there's two states sort of on one end of the spectrum. And California has been way out in front. We did a project for the Energy Commission a couple years ago on a guide for California communities of how to begin to adapt, laid out a process by which a community can begin to look at what's happened in the past, project future sea level rise, assess that community's vulnerability, map that, and then start to figure out where the highest risk areas is and how do we develop an adaptation plan. This just is one of the communities we looked at, which is Santa Barbara. I'm not going to spend a lot of time, but what we now have are very precise elevation maps, LiDAR maps, so we can now map where high water would be today. What if we increase that 24 inches by 2050, say, and put a 100-year flood on that? What if it goes up 5.5 feet, which is the maximum of the NRC report? How much of Santa Barbara gets covered? So those are beginning to tell us where the riskiest areas are. But some of those considerations are, what sea level rise do we use? Well, we have tide gauges. We now have some projections. We have the COCAT guidance document, the NRC report. But what's the lifespan of the facility? What's the cost of replacing it? And what's the impact or the consequence if we lose it or destroy it? And as one example is a public street or a parking lot. Another example is SFO. Those are very different structures, very different values and lifespans. And I'm just going to leave you with the Embarcadero again and a quote, which is from the Netherlands ambassador to the U.S., who's saying, "We can't continue to fight the water." Thank you. I love it when there's no questions.
Questions for Dr. Griggs?
So the last time I looked at an state's adaptation study, the planning parameters for sea level rise were something like 16 inches by 2050 and 55 inches by 2100. As a result of more recent research that's come out, either the IPCC report or anything else that's going on, do you see those planning parameters shifting?
Well, that's why I'm showing the ranges and then talk about depending on what your facility is. I think I don't see those changing any time in the immediate future, but I think it's a great example of what we might call adaptive management. The IPCC numbers have sort of just been released, and they're a little, I'll say softer. They're a little lower, but knowing how the IPC, what it represents, and they're a little more conservative. Values are in the same ballpark, a little lower for 2100. I think we should just be extremely cautious, but watch. Now that we have satellite altimetry, which is giving us numbers on a regular basis, we can, the last couple of years or even a decade, it's sort of leveled off for a while, but I don't think that should be a cause for complacency if you look at the long-term picture. So I guess the short answer is I would be on the conservative side when we're talking about large, expensive structures or public works projects. Because it also isn't that it stops at 2100. It's just where we are at 2100 because it's going to keep going for hundreds of years.
Any other questions?
Thank you very much.